Let us start today's lecture of soil dynamics. We are continuing with module 2 of vibration theory. So, we have understood the physical significance of high value of R or the DMF less than 1 when it can happen. Now, let me give its mathematical validation. I have given you the physical significance to understand the problem. Now, let me give you the mathematical validation, mathematically how we can prove this in a better way. If I give you, so using Maxwell diagram, we can again prove mathematically which zone is controlled by which parameter. We have f of t equals to p cosine of lambda t, and for which we got the steady state response x of t is x cosine of lambda t minus theta. That was the form of the solution, okay, some cosine function. So, the velocity is nothing but minus x lambda sine of lambda t minus theta, which we can write as x lambda cosine pi by 2 plus lambda t minus theta. So, that means the velocity is in the phase with the displacement with 90 degree, which is known to us. And what about the acceleration? X lambda square cos pi plus lambda t minus theta. So, acceleration is at a phase of 180 degree with respect to displacement. So, this is known to us from our high school physics. So, now what we can have three conditions. So, three possibilities can arise. The first one is when R less than 1, that is frequency ratio is less than 1, that means lambda is less than omega. We have theta less than pi by 2, that phase angle. The second case, R equals to 1, that is lambda equals to omega, theta equals to pi by 2. And the third case can be R greater than 1, means lambda greater than omega, theta greater than pi by 2. Let me draw the Maxwell diagram for all the three cases. The first case, if I want to draw the Maxwell diagram, what it will look like? Suppose this is our F s, which is equals to k x. I am now drawing the force diagram, okay? In Maxwell force diagram. This is our F x, F s, that is stiffness force equals to k x. Now, damper force F d will act 90 degree of this force, right, because that is a function related to the velocity. The damper force F d is nothing but c times x dot. So, that x dot is at 90 degree phase with respect to the displacement function. So, we need to draw now, let us draw this. So, this is now F d, the damper force equals to c x dot. It should be 90 degree phase with respect to the displacement function. Now, let me draw the inertia force F I. Inertia force will be m x double dot. Now, that x double dot acceleration is 180 degree phase with respect to the displacement function. So, this is our f I, which is m x double dot, this is also 90 degree, okay? And it has to be a closed polygon. So, this is our f of t externally applied to maintain the equilibrium of the system. And this angle is nothing but the phase theta, which is less than pi by 2. That is the first case. So, from this Maxwell diagram, this force diagram, what we can see, which force is maximum among these 4 forces? F s. Am I right? To make this angle theta less than pi by 2, which satisfies this condition, we need this force to be maximum among the 3. That is the meaning that this is a stiffness controlled zone. Is that clear? Now, why r less than 1 is called stiffness controlled region? Because as you go r less than 1, your stiffness force dominates. Let me put it back again. As you go r much less than 1, your stiffness region dominates. So, this we had understood physically, now we are understanding it mathematically. Let me see the other 2 cases. Before coming to the second case, let me give the third case first. For the third case, what we have? We have F s 90 degree to it, we have the damper force F d. Now, 90 degree to that we have F I inertia force, this is 90 degree, this is 90 degree and closed polygon. So, this will be our f of t with this angle theta greater than pi by 2. So, the third case, as we said, the phase angle theta will be greater than pi by 2. So, in this picture what we can see, which force is dominating? Inertia force is dominating, F I is dominating. So, that is why we call this case, that is r greater than 1 when we have lambda greater than omega. So, that theta greater than pi by 2 is called mass controlled zone. This is the reason, or this is the proof mathematically why it is called mass controlled zone, which we had already understood from this picture, why this region is called mass controlled zone physically. Physically we have understood the problem, now we have proved it mathematically. And obviously, the remaining parameter will control the second case, which is something like F s, F d, F I and F t with theta equals to pi by 2. This will be actually the damper controlled. As you have a control on this damping force, you will still it remain theta equals to pi by 2. So, the remaining one is damper controlled zone. So, this damper controlled guides you the DMF, which we have seen here. The peak value of DMF or maximum value of DMF is controlled by this damper control region. Okay. Now, let me discuss little bit about this phase. The phase I have used in the Maxwell diagram already, but I have not yet discussed about this phase, how it varies with respect to R and also different values of damping ratio. So, the discussion on phase angle. What is the solution we got? The steady state response to the static response is given by DMF times cosine of lambda t minus theta, where we know the tan theta we have defined as 2 eta omega by lambda square minus omega square, or 2 eta r by, I think it is the other way round, it was omega square minus lambda square. Yes. So, tan theta was 2 pi eta by omega square minus lambda square. So, we divide it by omega, we get it 2 eta r 1 minus r square. Okay. So, the expression for steady state displacement to static displacement was given by this, where tan of theta was defined as 2 eta omega lambda by omega square minus lambda square. That was the expression for tan theta, which we can simplify as 2 eta r by 1 minus r square. We have divided both numerator and denominator by omega square. So, here 1 omega get cancelled, lambda by omega is nothing but r, frequency ratio. So, now this phase, how it varies for different cases, let us see. So, when eta equals to 0, that is undamped case, we have the value of theta equals to 0 degree or 180 degree. When this is 0, tan theta 0 means it will be either 0 degree or 180 degree. So, theta is equals to 0 when r less than 1 and theta equals to 180 when r greater than 1, and for r equals to 1, theta will be equals to pi by 2. This is for the undamped case. Now, for damped case, how the variation occurs? So, when eta non-zero, that is damped case, for r equals to 1, what we are getting? R equals to 1, let us look back to the expression of tan theta. When r equals to 1, it is becoming infinity. So, obviously, theta is pi by 2. That is why, irrespective of value of eta, I have written earlier also, for r equals to 1, theta will be pi by 2. Fine. So, for damped case also r equals to 1 means theta equals to pi by 2, and r equals to 0 means, if we put r equals to 0 in this expression, we get theta equals to 0, and r tends to infinity means theta equals to pi. Fine. So, with these values, now let us plot this phase, variation of phase with respect to r. Like what we have seen the variation of DMF with respect to r, now we want to plot the variation of phase with respect to r. So, r, this is theta, at r equals to 1 we have some value r 0, theta varies between 0, then pi by 2 and pi. Let me draw some parallel lines first. So, it will be easy for us later on to draw different graphs. What we got when r equals to 0, theta is 0, and when r tends to infinity, theta goes to pi, and for undamped case, that is when eta equals to 0 degree, we got the value at theta equals to pi by 2 for r equals to 1. So, what will be the variation? It will follow this path, it follows this, this and this. So, this is the variation of phase for eta equals to 0, undamped case. But if eta is non-zero, then the variation goes like this. It starts at r equals to 0 is theta 0. So, from this point always it will start, and at r equals to 1 it will be always pi by 2. So, this point they must touch, and r tends to infinity, it becomes pi. So, all the variations will be like this. So, what we can write here, this will be in the order of eta decreasing. That means, it can be eta say 0.1, it can be eta 0.2, this can be eta 0.3 like that. So, 0.3, 0.2, 0.1 and eta 0. So, that is the way the phase is varying with respect to the frequency ratio r. So, now the same thing what I have just now explained, let us look back to the slides here. The DMF variation we have seen already. This is the variation of phase angle with respect to frequency ratio, as I have explained, 0 degree, 90 degree and 180 degree. It always pass through this point when r equals to 1, frequency ratio is 1, the phase angle must be 90 degree. When r equals to 0, phase angle is 0 degree, and r infinity it tends to go to pi. So, this is the variation, and this is the decreasing trend of the damping ratio. So, this is high value going to the lower value. Okay. Now, let us come to the next subtopic, the forced vibration due to imbalance of mass. Let us look at the sheet now. So, forced vibration due to rotating imbalance. So, what does it mean? Let us draw a picture, that is, suppose we have a big machine with a mass say capital M, and this is the CG of the machine, big machine, and there is a rotating component of a mass, that is a small mass of m, small m, it is rotating continuously within that machine. So, it is having some eccentric mass with respect to its own CG, which is keep on rotating, fine. So, let us say this is the value of the eccentricity E and this frequency with which it rotates is lambda. Okay. So, this angle I am expressing in terms of lambda t, and this magnitude of eccentricity of that small mass with respect to the CG of the main machine is E. So, this is the eccentricity with which it rotates. Now, as usual, I have the single degree of freedom system we are considering, stiffness and damper. We have x of t with respect to the CG of the main mass. And what we said, capital M is the total mass of the system, that is mass of the main system plus mass of the main system plus eccentric mass. Okay. So, capital M is the mass of the entire thing including that eccentric mass, whereas the small m is eccentric mass. And what is the condition? This small m is much lower than this capital M. Obviously, a small eccentric mass is rotating, as I have explained already. So, what will be our equation of motion for this system, this single degree of freedom system? Let us see. So, if I try to draw the system once again, about this CG, I have rotating mass here with E, this angle is lambda t. So, what is this value? This distance E sin of lambda t, am I right? And our x is measured with respect to this reference point x of t. So, if I want to write down the equation of motion for the entire system, what it should be? The main system, it's having how much displacement with respect to its CG? X t, excluding the eccentric mass. So, excluding eccentric mass, the main system is having an acceleration of x double dot. So, I have the inertia force m minus m x double dot. This is the total mass of the system. If I exclude that eccentric mass, that is subjected to acceleration of x double t, x double dot. So, the inertia force is m minus m x double dot plus this eccentric mass is also rotating. So, it is also subjected to an acceleration. Now, this eccentric mass is subjected to how much of displacement? Not x of t, but x t plus E sin lambda t. So, the acceleration this eccentric mass is subjected to will be, so the inertia force, if I want to write small m times d2 by dt square, the displacement which is x plus E sin of lambda t. Fine, because this eccentric mass is subjected to this displacement, I can get the acceleration by double differentiating it. So, acceleration times mass will give me the inertia force coming because of this rotating imbalance, mass imbalance, plus the remaining things as usual, C x dot plus k x, because they are subjected to with respect to the C g of the system. So, that is why C x dot only and k x only. Fine. This is equals to how much? There is no other externally applied force to the system. So, it should be equals to 0. Fine. So, now if we want to simplify this expression, what we can get? Let me do it, put it little above, so that it will be easy for us to follow. So, now I am simplifying it further. Capital M x double dot minus small m x double dot plus, from this I am getting small m x double dot minus, I have to differentiate this twice with respect to t. So, I am getting sin to cos, cos to sin with minus sign. So, m e lambda square sin of lambda t plus c x dot plus k x equals to 0. Now, this gets cancelled. We can simplify it further, m x double dot plus c x dot plus k x equals to, it comes to right hand side, m e lambda square sin of lambda t. So, this is the governing equation of motion for a system, single degree of freedom system subjected to eccentric mass rotating imbalance. So, look here, the dynamic load is coming from the moving parts of the machine or the rotating parts of the machine. So, that is why we have mentioned in the very first class that the reason of generating dynamic load, one of the reason is this rotating part of a machine, machinery body or something like that. So, this is nothing but again a harmonic load. So, what does it mean? Already we have solved what is the solution for a single degree of freedom system subjected to a harmonic load. So, this we can further simplify, that m x double dot plus c x dot plus k x equals to q sin of lambda t, where this amplitude q is measured as that rotating mass small m eccentricity of the mass with respect to the C g of the entire system and the frequency with which the rotation is occurring. So, external frequency. So, m e lambda square gives us the magnitude of this q. So, solution for this is already known to us, no need to go through again the solution, because single degree of freedom system subjected to a harmonic load, what is the final solution we know now. Let us use that, and we are interested about the steady state displacement as we have already talked about. So, I am writing limit when t tends to infinity, our x of t, the total dynamic response, it is written as steady state displacement, which comes out to be, earlier it was p by k, right. So, now it is q by k sin of lambda t minus theta. Earlier we had taken the cosine function harmonic, now it is a sine function. So, it will be sin of lambda t minus theta. Fine. Let me take this equation once again for you. Yes, this divided by root over the same thing 1 minus r square whole square plus 2 eta r whole square. So, that is our x of t, which we can rewrite again or simplify it further like this, or x s t, the steady state response is x sine of lambda t minus theta. What we did earlier also, the same thing we are doing here, all where this capital X, is nothing but q by k by root over 1 minus r square whole square plus 2 eta r whole square. Now, let me put the expression for this q and k. Q is how much? M e lambda square. So, m e lambda square, and how much is k in terms of m and omega? K is m omega square. Fine. In that case, it has to be the total mass, of course, divided by root over 1 minus r square whole square plus 2 eta r whole square. So, this if we want to simplify further, what we will get? Look at here, lambda square by omega square. So, this is r square, and the rest of the term, the small m e and capital M, we will take on the left hand side. So, what I am telling you, so I am simplifying it like this: x capital M by small m e equals to r square by root over 1 minus r square whole square plus 2 eta r whole square. Fine. This term x m by m e is known as DMF, dynamic magnification factor, for this case of rotating imbalance, that is a moving rotating body which is eccentric with respect to the C g. So, this term, so this is our expression for dynamic magnification factor for a rotating mass, whereas earlier the expression was 1 by this. So, here there is a slight change in the numerator, we have now r square. So, that is the difference of DMF with respect to the previous case. Now, let me plot this DMF with respect to r again. What we did for the previous case, we want to do here also. Now, r, this is, I am plotting x m by m e, which is expressed as DMF here at 1, 0, 0, 1. Let me draw this parallel lines first. It will be easy for us to draw the graph and understand the condition. Now, when r is 0, what is the value of this x m by m e? Irrespective of value of the damping ratio, whenever r is 0, this is 0. So, it starts from this value 0, 0 always, and when r is very, very high, tends to infinity, what happens to this x m by m e? Whatever be the value of the eta, this is infinity by infinity. So, it will tend to approach to 1, right. So, it starts from here and goes to 1, and when eta is 0, at r equals to 1, what is the value of x m by m e? When eta 0, this is vanished, r equals to 1. So, this is 0, I get infinity. What does it mean? For eta 0, that is undamped case, the variation will be something like this. It approaches infinity, it comes from infinity, and here it approaches 1. That is the variation for eta equals to 0, undamped case. And if eta is non-zero, obviously this value will not be 0 even if the r equals to 1. So, we will get some variation like this. So, starting point is always same 0 0 and end point approach is always same, approaching to x m by m equals to 1. These are the in the order of eta increasing, that is say eta 0.1, then this is eta 0.2, then this eta 0.3 like that. And where this maximum value of x m by m e occurs, the same case like previous one, we want to find out where the maximum DMF occurs. If you look at the figure carefully, already I have drawn this occurs little after r equals to 1. So, let us see where it occurs now mathematically. So, we want to find out now maximum value of x m by m e where it occurs. So, x m by m e max for what value of r that we want to find out. That means, we do this operation again. Equals to 0. If we do this from the expression of this x m by m e, differentiate this term with respect to r and equate it to 0. On simplification, we get r equals to 1 by root over 1 minus 2 eta square. That is the value of r where this becomes maximum. And what is the maximum value of that x m by m e? If you put in this expression the value of r equals to this much, whatever x m by m e you will get, that is the maximum value, like previous case only. So, x m by m e max, if you put this, you will get 1 by 2 eta root over 1 minus eta square. If you compare these two values, what you will get? The maximum value, the magnitude of dynamic magnification factor is same whether it is subjected to a forced vibration with harmonic excitation or it is subjected to the forced vibration due to a rotating imbalance in the system. Maximum dynamic magnification factor remains same, but the location, that is for what value of r that maximum occurs, that differs. Earlier it was little before 1 r equals to 1, that is little less than r equals to 1. Now, it is little above r equals to 1. So, r little bit greater than 1 it occurs. So, it is again the reciprocal of the previous case. Earlier r was root over 1 minus 2 eta square and now it is 1 by root over 1 by 2 eta square. As all our cases of eta are less than 1, so obviously, this r is becoming little greater than 1, right. So, that is why I have plotted already that these peaks are occurring at little after r equals to 1 in this graph. So, if I want to plot it for a damped case, it should look like this, that the variation of r x m by m e I have this as r equals to 1, this as 0, this as 0, here it is 1. So, the variation for any damped case is like this, where I have this maximum value occurs at r equals to 1 by root over 1 minus 2 eta square, and this magnitude of maximum value is 1 by 2 eta root over 1 minus eta square. And how the phase varies? If we look at the expression, the phase will vary in the same manner, because this is also the function is harmonic in nature. Let me put back the equation once again for you. So, this variation is again harmonic. So, if you see the variation of the phase, let me draw it here itself. The variation of the phase will be something like the similar one, that r theta 0 r equals to 1, this is 0, pi by 2, this is pi, at eta equals to 0, that is undamped case, it follows this. So, this is my curve for eta equals to 0, and for eta non-zero, it follows this trend. So, these are decreasing eta with say eta 0.1 here, eta 0.2 here, eta 0.3 like that. So, variation of phase remains the same like the previous case. Okay. So, now let us look at the slide. What I have explained and derived just now, force of excitation due to rotating imbalance, picture shown. This is the rotating mass which is rotating about the CG with an eccentricity of E. M is the mass of the total system. The equation of motion, governing equation of motion expressed like this, from which the solution we get like this, and the variation of that x m by m e is given like this, with peak values coming here with respect to the frequency ratio for different values of damping ratio. Also, the phase angle, how it varies the same way like the previous case with respect to the frequency ratio. Now, for DMF is equals to 1 by 2 eta for r equals to 1, when the maximum occurs, just now we have derived, it occurs at 1 by root over 1 minus 2 eta square, and that maximum value of DMF is the same like the previous case, that is 1 by 2 eta root over 1 minus eta square. Let me come to now another subtopic, which is called half power bandwidth method. This is another experimental method to determine the damping ratio of any system. Earlier we have seen the logarithmic decrement has been used to measure the damping ratio of any system subjected to damped free vibration, right. So, if any system subjected to free vibration and we do the testing, in that case we measure the damping ratio using the concept of decay of motion or logarithmic decrement. Now, using the concept of forced vibration also, we can measure experimentally the damping ratio of any system. This is the way, the half power bandwidth method, by which experimentally we can obtain the damping ratio of any system. How? Let us look at the slide. So, DMF versus different applied frequency. This is actually our lambda what I am using in my derivation. Okay. These are exciting frequencies, different exciting frequencies. We get a plot like this. It starts from 1 goes back to here subjected to a harmonic excitation. We have a maximum DMF here and we can identify one value of DMF which is equals to DMF max divided by root 2. So, that value will obviously occur at two externally applied frequency values. Let us say one is lambda 1, another lambda 2 in terms of our notations. This is for very small value of damping ratio. For very small value of damping ratio, we can approximate the maximum damping dynamic magnification factor is equals to 1 by 2 eta, right. Let us look at this sheet. The maximum value of damping ratio for very low value of eta, we can approximate it as 1 by 2 eta only, fine. So, that is what it is done in the slide. Let us look at here again. Now, for r equals to 1, when frequency ratio equals to 1, what we can express the dynamic magnification factor maximum value. Now, we are dividing it by that root 2 term. So, that is given by 1 by 2 eta. So, now we are dividing it by root 2. So, in denominator we are getting root 2, which is given by this expression. So, for two different values of r it can occur. So, from this second order expression for r, what we will get 2 roots of r. If we solve this, we will get 2 values of r, which is obvious that this value will occur at 2 values of r. So, that is what on simplification, if we express this almost equals to 1. So, on simplification we are expressing lambda 1 plus lambda 2 by 2 times of natural frequency almost equals to 1. Then the damping ratio is given by that lambda 1 minus lambda 2 divided by 2 omega. So, in our terminology what we are using, let me express it once again for you. What we were mentioning, the DMF, this is say applied frequency of excitation lambda, we have from here to a maximum value, then slowly comes to almost 0. We have a DMF max here and we have these two values lambda 1, lambda 2 for DMF max by root 2. And putting in the expression what we got, that damping ratio eta is given by that lambda 1 minus lambda 2 divided by 2 omega natural frequency. This lambda 1 minus lambda 2, this is called half power bandwidth. So, this is that is why the name came half power bandwidth method to obtain experimentally the value of the damping ratio. Okay. So, with this half power bandwidth method, we will complete our lecture today. We will continue our lecture in the next class.